Hi friends, welcome to our channel Bright Education Center. In this video, we are going to discuss about the topic thermal properties of matter. It's a chapter prescribed in grade 11th physics syllabus. We are going to analyze major concepts and equations which will help you for your competitive examinations like Neet or JEE and SAT exams. Please follow the lessons clearly, refer your NCERT textbook also, and get ready with the topic for your upcoming exams. So wish you good luck in your exams. We can start like this. So in this topic mainly the thermal properties of matter. That means if you provide heat to a substance, then how do this substance will behave? Like what changes or will take place there? How much heat you can provide to a substance? Or if you give sufficient heat, is there any change for the substance happens? These all things we are going to discuss in this chapter. So mainly heat and its after effects as the aim of the chapter. While you study about the heat, while saying two words, heat and temperature, these two terms are significant meaning or role for this chapter. Heat means the total energy contained in a body, we can say. A simple way of saying what is heat. The total amount of energy contained in a body is called heat. And temperature is a measure of hotness or coldness of a body. How much hot a body in compared to other. That's called temperature. So by measuring temperature, we can know that whether the body have more heat or less heat. So temperature help you to identify how hot the body is. That's the difference between heat and temperature. To measure heat, we have calorimeter. We have the unit calorie or joule, you can use the units to measure the heat of a body. But to measure temperature, we have thermometers. Different temperature scales are there. So one of the initial topic for the chapter is how to convert from one temperature scale to another temperature scale. Most common scale is Celsius, and clinical we use Fahrenheit, and the SI system is Kelvin. Then other is numerical. So like that scales we have. So what is there common for them? All this scale is based on the melting point and boiling point of water, and how many divisions they use in between the melting point and boiling point. Melting point or freezing point also you can call it as. So the minimum and highest, this temperature two scales, these two reference point they utilized in these scales. Out of this any temperature scale you take, there is a constant, a ratio is constant there. Using that concept, you can convert from one scale to another scale. Like this way the ratio you can see, the reading on the scale, theta I am calling suppose, minus theta 0, the freezing point or the melting point of water based on that scale, divided by total number of divisions of the scale. Divisions means between boiling point and melting point or freezing point, theta m minus theta 0. This ratio will be a constant for all the scale. So for Celsius, you can say like this way, Tc, the temperature in the Celsius scale, minus 0 degree Celsius is the freezing point in Celsius scale, divided by 100. 100 means 100 degree Celsius is the boiling point minus 0. So 100 minus 0, you get this ratio for the Celsius scale. Tc minus 0 by 100, that is nothing but Tc by 100. Same ratio if you do in Fahrenheit scale. In Fahrenheit, TF, the given reading minus 32 degree Fahrenheit is the freezing point of water in Fahrenheit scale, 32 degree Fahrenheit. And 212 is the boiling point. So 212 minus 32, that is 180. So there are number of divisions, 180 divisions are there. That is in Fahrenheit scale. And Reaumur scale, it is TR minus 0 by 80. And in Kelvin scale, it is Tk minus 273 by 100. So in both Celsius and Kelvin scale, number of division between melting point and boiling point are same, 100. So any of these two, suppose a temperature is given in Kelvin, you want to convert to Celsius, then you can use this component. Tk minus 273 is equal to Tc, because 100 and 100 cancels. Or in a Fahrenheit scale, it is given one temperature, you have to convert to Celsius. Or Celsius is given, you have to convert to Fahrenheit. These two relations you can use it. So like that, corresponding ratios, if you equate, then you can convert from one scale to another scale. One question is to get from that idea. Or sometimes question will be like this way, a faulty thermometer shows this much reading. and the actual reading what will be based on the centimeter scale or Fahrenheit scale or Celsius scale, like that it can be asked. There also you can use it. And one logic idea, this Fahrenheit scale and Celsius scale become equal at negative 40 degree. So negative 40 degree Celsius will be equal to negative 40 degree Fahrenheit. So in that particular temperature, this both become equal. And almost 1 degree Celsius increase, 1 degree increase in Celsius scale will make almost 1.8 increase in this Fahrenheit also. So that logic you can utilize in the calculating when it convert from one scale to another scale, or one set of reading to another set of reading. I hope you got it. So please be thorough with that one. Now, so that's about the temperature, the basic idea about how to use this temperature scale to different ways. We are going to the topic like, if you provide heat to a solid body, what all changes may happen? The primitive or the primary change will be an expansion, means an increase in its dimension, either maybe in length or maybe in area or maybe in volume. So this in common is called as thermal expansion. The body will expand, solid will expand. That in chemical level you can go to the bond length and all will be changing, expand, because of that expansion is there. So if there is a length increase is there or increase in length is there, we call as linear expansion. It says that the fractional change in length, that is increase in length by original length, will always be directly proportional to change in temperature. We will say about it, delta L by L is proportional to delta T. Delta L by L is a fractional change in length, will be directly proportional to change in temperature. That's sure, of course. So based on the original length only the change will be there. There you are getting a constant called a coefficient of linear expansion, we present alpha. So if you convert to equation, then alpha you can get is delta L by L into delta T. This will be constant for a particular solid. So for each different metals, it have different values are there for this alpha. Some have higher value, some have lower value. That means some are resistant to heat, some are more, what you can say, favorable to the heat, like that. Easily you can get a expansion in that materials. Different materials have different properties are there. So while doing the numerical questions, it will be provided for you what is alpha. Okay, you can see here delta L by L, its units get cancelled, so dimension get cancelled, and delta T temperature. So per Kelvin, Kelvin inverse is a SI unit of alpha, the coefficient of linear expansion. Similarly, we can do area expansion and volume expansion. In area expansion, we have a coefficient called beta, the coefficient of area expansion of a solid. Beta is equal to change in area by original area into change in temperature. That is fractional change in area divided by change in temperature. That will give you the coefficient of area expansion. And you can have the coefficient of volume expansion also. The change in volume with respect to original volume, that is fractional change in volume, is proportional to change in temperature, delta T. So from there also you are getting a constant called gamma. We can express gamma is equal to delta V by V into delta T. That is fractional change in volume divided by change in temperature. So here we are getting three constants, alpha, beta and gamma. For a solid, these three behavior you can expect. So if you provide the heat so that its length can change, its area can change, or its volume can change. Alpha, beta, gamma. So that's the first effect of a solid when you provide heat to the body. These three, alpha, beta, gamma, are related like this way. Alpha will be equal to beta by 2 and that again equal to gamma by 3. Gamma by 3 will be there. So this gamma will be 3 times alpha. Volume expansion will be 3 times linear expansion and area expansion will be 2 times the linear expansion. So this ratio will help you to to link these three coefficients, alpha, beta, gamma. So once more, while you're providing heat to a solid, there is chance of 3 expansions, linear, area and volume. 3 coefficients we have, alpha, beta, gamma. This way they are related. Now, a concept, how much heat you can provide to a body. You know, of course, for every body, as much heat you need, that much we cannot provide for a body. It depends upon their mass and their capacity to hold the heat. So a term specific heat capacity is a standardized value of heat. 1 kilogram of a substance. Suppose you want to increase its temperature through 1 degree Celsius or 1 Kelvin. Then how much heat it can be absorbed or provided. That is called a specific heat capacity. So it is the amount of heat absorbed or released. In both cases, temperature can change. So to change the temperature through 1 degree Celsius for a unit mass of a body. Specific heat capacity. So why we made mass constant means, for example, 1 kilogram of ice or 3 kilogram of ice. This both are ice only, but their amount is different. They can hold different amount of heat, or they require different amount of heat to convert to water, or they can release that much heat, that we can say. Different objects have different specific heat capacity. Based on that, you can get a chart also, and we are standardizing that unit as specific heat capacity. S is equal to 1 by m. M is the mass of the body, delta Q by delta T, where delta Q is the quantity of heat supplied by change in temperature, delta Q by delta T. This equation will help you to calculate how much heat is required to increase this much temperature for a particular mass of the body. Then if S is given, you can use it. Delta Q is equal to S into M into delta T. You can rearrange the equation. The SI unit of specific capacity is joule per kilogram per Kelvin. That's the SI unit of specific heat capacity. Now, if you come to the gases or fluids mainly, we'll express its mass or the quantity in terms of moles. Then we have molar specific heat capacity. The amount of heat absorbed or released for a 1 mole of substance to change its temperature through 1 degree Celsius or Kelvin, we call as molar specific capacity. C is equal to 1 by mu, where mu is the number of moles, into delta Q by delta T. So amount of heat supplied by change in temperature. This molar specific capacity also have the unit joule per mole per Kelvin, because mu gives you the number of moles. So more number of moles, it need more heat to change the temperature. So range of temperature is a fact. How much it can hold it, like that. Okay. So these values will be constant for a particular material, the specific heat capacity. Now heat capacity or thermal capacity, if you say, then if you know the heat capacity, specific heat capacity, if you multiply with its mass, you can get the thermal capacity of a body. This thermal capacity help you to know how much it is required for this much of particle to convert or to increase the temperature. The thermal capacity. So here we got how much heat you can supply to a body. That depends upon the nature of the body also, the amount of the body also, change in temperature also. These all things. Now next level. Suppose you give sufficient heat to a body, then it is found that the body, the matter will try to change its state. So change in state may take place there. So initially I told you, if you give heat to a body, it can undergo an expansion. 3 modes of expansion we discussed: linear, area and volume expansions. Now again you increase the flow of heat to the body, then its change may state. Solid may become liquid, liquid may come to gas. If you increase the heat, and if you allow them to cool, means if they release the heat, gas will come back to liquid, liquid will freeze to solid. This is also known as, if solid to liquid is going on, melting, or we'll call it as, altogether we can go as freezing and melting. These are the 2 ways forward and backward change. And liquid to gas, we can say vaporization is there, or boiling will call as the concept. Remember this backward, even solid to gaseous directly or gas to direct to solid, sublimation we have. This whole process you might be going on through the lower class level. And the 2 temperatures, melting point and boiling point, are 2 important. Melting point is the temperature at which both solid and liquid phases are in thermal equilibrium. So at 0 degrees Celsius, both ice and water will have same temperature. That is the temperature at which ice start to melt into water. Similarly for different solids it have. And one idea, latent heat. I have another crucial rule for it. The amount of heat required or absorbed by a material during the transition time. That means while changing from ice to water, or solid to liquid, or liquid to gaseous, how much heat they absorb. During that time there is no increase in temperature. So while you're providing heat to a body, normally it used to increase the temperature of the body. But during transition or change in state, it's required to change the state. That amount of heat is called a latent heat. L is equal to Q by M, where Q is the quantity of heat supplied by mass, Q by M. That is L. So there you can substitute. If you know L, then how much heat is required to convert this much kilogram of a body, then Q is equal to M into L. You can use that equation also. So latent heat, L have the unit joule per kilogram. One idea. So melting point, boiling point and latent heat. And one more significant point there, this melting point and boiling point both changes with respect to pressure. As pressure you increase, the melting point decreases. That means ice will melt before reaching 0 degrees Celsius. That means at a negative temperature itself, you can melt ice if you increase the pressure on the ice. And for a boiling point, if pressure increases, boiling point also increases. That benefit we are getting from pressure cooker. In the pressure cooker, pressure will be very higher, so water will be boiling at a temperature higher than 100 degrees Celsius, so that the food materials which is mixed with that boiling water will be cooked easily. If water have sufficient heat to be cooked, then it will be easy cook. That's the benefit we are getting from the pressure cooker. At high pressure, boiling point increases, but melting point decreases. Please keep that point also. Now, if two hot bodies, one hot body and one cold body, at different temperatures, two bodies you combine together, there will be flow of heat. The principle of calorimetry will help you to find how much heat is required or how much heat is lost. Principle says that the heat lost by one body will be equal to heat gained by another body. So, this much of, for example, how much heat is required? Question comes to change this 3 kilogram of ice to a water at 10 degrees Celsius. So, first its temperature is increasing, then reaching at 0 degree it melts. During melting, it absorbs heat in the form of latent heat, then it converted to water, then again increase in temperature of the water. So this 3 process happens there. Initially temperature of ice increases, first process, then ice melt, second process, then third water's temperature increases. In these 3 acts, total heat required. We can use this calorimetry. Heat lost by a body is equal to heat gained by the other. Then heat loss you can get from this idea, delta Q is equal to Sm delta T. So here this H or delta Q will be equal to S into M into delta T. So if you know specific capacity, then you can multiply the mass and change in temperature. How much heat is absorbed? The same will be equal to lost by the other body. That will help you to calculate this one. One sort of question you can expect from this part too. Here, change of state we got it. Now, which all ways you can provide heat to a body? We have mainly 3 ways transfer of heat to a body. Either you can do method of conduction, or you can do the method of convection, or you can do the method of radiation. Mainly in these 3 ways, the heat is transferred from one body to another body. For example, from sun to earth, the heat we get in the form of radiation. There is no need of any medium for the electromagnetic waves carries this heat to our earth. Infrared radiation we have, ultraviolet radiation we have. Microwave oven, microwave waves are used to the radiation is there. Now convection is there. The real movement of hot particles or cold particles. Air conditioner, AC works on this principle. In a room, the hot particle itself move to one up, at the time cold particle come down. Actual movement of the particle happens. Through the hot water, water boils from bottom onwards. So the boiled water molecules comes up. That way throughout the water it gets hotter. Then we have conduction. Due to contact between the bodies, 2 bodies, the heat moves. There is no movement of particles actually, but due to presence or contact between the 2 bodies, the heat moves. While moving through contact, then the rate of flow of heat H is given by, means Q by T, delta Q by T, time. So per second, how much heat is transferred is equal to Ka into T1 minus T2 by L, where K is thermal conductivity of the material. It's a constant. A is the area of cross section of the body or the contact where it's done. T1 minus T2 is the change in temperature difference between 2 ends of the body. Body may be a rod, for example. Divided by L is the length of the rod. So 2 bodies are connected with a rod. One end is at temperature T1, another is at T2. Then the rate of flow of heat depends upon difference in temperature. Suppose huge difference is there in temperature, fast rate movement will be there. The area of cross section is higher, more flow will be there. And length, if length is longer, then it will be inversely proportional, means slow rate will be there. So these three factors it depends upon. This will help you to find K also. Area or change in temperature, you can rearrange it. So this rate of change of flow of heat, H has the unit joule per second, okay. So amount of heat flowed per time, joule per second. It has it. Area half meter square, L half meter, then change temperature to Kelvin. You can use the concept. Okay. So you got what is thermal conductivity? K, a term you got it. Now, what is the dimension of conductivity? K is actually mL T power minus 3 K inverse. This K for Kelvin, time, length, mass. Thermal conductivity. Okay. From this term, one idea you can get thermal resistance of a bar, of a rod. RH is equal to L by Ka. Where K is the thermal conductivity again here. So thermal conductivity is opposing concept. The thermal resistance. RH is equal to L by Ka, you can say about it. So in conduction, the rate of flow of heat through a rod is directly proportional to the area of cross section and inversely proportional to length, and is again proportional to the change in temperature we got it. So that's about the conduction. So during conduction, because of contact between two particles or two bodies, the heat transfers. Now in radiation, we have black body radiation mainly. In radiation, we have some laws. How much energy is radiated per second or per area. This all depends upon the temperature of the surface also. One of the important law is Stefan-Boltzmann law. The energy radiated E is equal to sigma into T power 4, or the energy radiated per unit area is proportional to fourth power of the temperature, absolute temperature of the body, T. So a constant sigma we are getting called Stefan's constant is equal to 5.67 into 10 raised to minus 8 watt per meter square per Kelvin power 4 minus 4. So here Stefan's law, E is equal to sigma T power 4. So black body radiation, a concept, a perfect black body, say a good emitter of this radiation. If it is not a perfect black body, then you can use this equation, E is equal to E into sigma T power 4. But this small e shows the emissivity. For a black body radiation, emissivity is 1. So for if it is not 1, then it will be less than 1. E will be between 0 and 1 for a non-perfect black body. Now, what is the emissive power? It is the energy emitted per unit area of the substance, of the body, we can say, E. And this E, and absorption power or absorptivity, we can say A. This ratio will be always a constant. So we can say a good absorber of radiation will be a good emitter of radiation also. Kirchhoff's law says that E lambda by A lambda will be always a constant at a particular wavelength. If a body absorbs a particular wavelength of radiation, then it can emit that wavelength also the same way. So E lambda by A lambda will be a constant. E for emissive power, A for absorption power. So coefficient of absorptivity also we can say at a particular wavelength will be a constant. So a good absorber is a good emitter of radiation also. You will get that idea. Now, Wien's displacement law, it says that the product of wavelength, maximum wavelength of radiation which can come to into temperature is always a constant. That Wien's constant will call us. Wien's constant is 2.9 into 10 raised to minus 3 meter into Kelvin. So lambda m, the wavelength, the maximum wavelength which is emitted from a body is inversely proportional to the absolute temperature T, or their product is always constant. A concept that's of the radiation we can get from Wien's displacement law also. So here we got two modes of transfer of heat, conduction and radiation. I hope you understood it. Now in convection, there is, I told you already, actual movement of particles is there. So because of that we have some effects like sea breeze, land breeze and all. When land side is higher temperature, then heat means the hot wave, hot air is moved upward from the land surface. At that time the cold air from sea surface come towards land. And during evening time, after evening time, the air or the sea water is hotter than the land, because the specific heat capacity of water is the highest. But for sand it is less. Water will take much time to cool down and much time to heat up also. So soon after sunset, land become colder first, then only sea water will come. So at that time the air from sea level, I mean water level will go up, so cold air from land will move towards sea. This way land breeze and sea breeze forms. It's an example of convection. So movement of hot air particle, that's example of convection. That happens because of temperature difference. Okay, fine. So three modes of transfer of heat: conduction, convection and radiation. Regarding radiation and conduction you have these concepts also. So please take care about these topics too. Now for a hot body, how do the energy moves from hot body to the surrounding? We have Newton's law of cooling. According to his statement, he says that the rate of flow of heat from a hot body to surrounding, or in simply we can say the rate of cooling, energy lost per time dq by dt is always directly proportional to the difference in temperature of the body and surrounding, where T is the temperature of the body and T is the temperature of surrounding. So for cooling, of course, temperature, surrounding temperature will be less than T, and as the time goes this rate will be decreasing. Okay, so if this difference is higher, then fast rate of cooling will be there. If it is small, the difference is lower, then there will be low rate of cooling. It will take long time to cool down. This we are getting from Newton's law of cooling. K is a constant of proportionality here. So by using this concept, we can get at what rate a body cools down or how much time it takes. You can differentiate it, or you can rearrange and make the time taken to cool down. Also you can use the concept. How much time it will take to cool from this to another temperature. By using this concept, you can do it. So here we got this concept. Now a topic we discussed about thermal expansion of solids. Now in liquids, how it happens. For gases we have another topic, kinetic theory of gas, that we will discuss in detail. For liquids, thermal expansion in liquids, we have coefficient of real expansion gamma R is equal to delta VR by V into delta T. So real expansion and apparent expansion, two expansion will be there for liquids. Because if liquid taken in a container and you heat up, the container also expands. Because of that, an apparent expansion of volume is there, and real expansion of volume also will be there for the liquid. So coefficient of real expansion gamma R is equal to real expansion of volume delta VR by original volume into change in temperature or increase in temperature. Now coefficient of apparent expansion gamma A. For apparent expansion, gamma A is equal to delta VA, the apparent expansion of or apparent increase in volume or apparent expansion of volume divided by original volume into increase in temperature. And if gamma G is the container's coefficient of volume expansion of the container, then gamma R is equal to gamma A plus gamma G. The coefficient of real expansion will be equal to coefficient of apparent expansion plus coefficient of volume expansion of the container, gamma G. The relation is there. So that happens for the liquids in this case. So how we got these topics? We done what is how to change the temperature scales between what is thermal expansion in solids and in liquids. We got it. And how the change of state happens. Got it. And now the mode of transfer of heat also, three modes of transfer of heat is there. In between we got to some terms like latent heat, specific capacities. So these all topics you make sure pause the video and prepare well, then we can do some numerical questions. We can do a question like this way. A metal plate 4 mm thick has a temperature difference of 32 degrees Celsius between its faces. It transmits 200 kilocalorie per hour through an area of 5 centimeter square. Thermal conductivity of the material is. So that's the question here. In this question we have thickness is given of the face is 4 millimeter. L is equal to 4 millimeter we can say. That means the length we can consider like this way. That's equal to 4 into 10 raised to minus 3 meters. Then we have area of cross section also. A is equal to 5 centimeter square is given. That is 5 into 10 raised to minus 4 meter square. Centimeter square you have to convert to meter square. Then we have the temperature difference delta T is equal to 32 degrees Celsius. So if the difference is given, then no need to convert to Kelvin because both have same divisions. If individual temperatures are given, you take care always you should use to Kelvin. Okay, if ratio or like that also comes individual, then you have to convert to kelvins, is sure. If difference given, then no need to convert to Kelvin. It can be kept in Celsius itself. Then heat transmitted per hour is given. So per hour heat transmitted H is equal to, we have 200 kilocalorie per hour is given. So that's you have to convert to joule per second. Okay, so kilocalorie per second you have to convert. That will be 200 into kilo means 1000 into calorie means 4.2 joules you have to convert. That's divided by per hour means hour to seconds. 60 into 60 can do that much joule per second. If you want, you can solve here itself, or you can do the next case also, no problem. It will be almost, will become 233.3 joule per second will come if you do this one, H. Now we have to find the thermal conductivity K. So we have the equation that H is equal to Ka into delta T by L. From that equation we can have K is equal to H into L by A delta T. These all terms we have here now. H also we have, L, A and delta T. Just substitute and you can do like this way. So this will be equal to almost K is equal to H we have 233.33 into L we have 4 into 10 raised to minus 3 divided by A, area is equal to 5 into 10 raised to minus 4 into delta T, the change in temperature is 32. If you do this calculation, just divide it, the power terms and all, you will get almost 58.33. That much watts per meter per degree Celsius. So here the option is A, the answer. Okay, so here how the conversion and how to find the thermal conductivity. I hope you got it. But another question we can do like this. The temperature of 100 gram of water is to be raised from 24 degrees Celsius to 90 degrees Celsius by adding steam to it. Calculate the mass of the steam required for this purpose. In this question, we have to use the principle of calorimetry. So you have to add steam to water so that water's temperature should be increased from 24 to 90 degrees Celsius. You know, steam will be at 100 degrees Celsius. So steam will lose heat and water will gain heat. So in this process, we can say 3 steps are there. First of all, steam should convert to water at 90 degree. We have latent heat there. Then from 100 to 90, its temperature should be decreased, that is hot waters. That much heat will be absorbed by the water from 24 to this 90. So here the things are given like this. Heat lost by steam will be equal to heat absorbed by water. The concept you have to use it actually. So heat lost by steam means there will be 2 heats, we can say. One, latent heat of steam to convert this way. That will be, suppose M1 is the mass of heat, steam is there. M1 into L will be the amount of heat absorbed by steam during conversion to water, steam to water. Then that water will have 100 degrees Celsius. Then its amount of heat absorbed by that water will be M1 into S into change in temperature. That will be from 100 minus 90. Because steam converted to hot water, then hot water 100 to 90 becomes. That much will be the heat lost by steam. So 2 processes happen there. Will be equal now heat absorbed by the water. And I am putting M2 with the mass of the water is equal into S into its temperature change from 24 to 90. So change will be 90 minus 24. That is the equation what you can give. Now latent heat of this stream is equal to 540. You can take it M1. 540 into M1 plus 100 minus 90 is here into 1 is M1. That will be 10 M1 is equal to 90 minus 24. That is 66. 66 into 1 into M2. So 66 M2 you can put it. So that will be 500, 540, 510, that will be 550 M1 is equal to 66 M2. You have to find M1 actually. So M1 is equal to 6 into 100 grams of the water M2 already be equivalent. 100 grams water actually you have to increase the terms, divided by 550. So if you divide it, it will become almost 12 grams. So we need 12 grams of steam to convert the water's temperature from 24 to 90. So this concept is very important principle of calorimetry. Heat lost by hot body will be equal to heat gained by the cold body. Okay, I hope you got it. So a question like this, a black body at a temperature of 227 degrees Celsius radiates heat at a rate of 5 calorie per centimeter square second. At a temperature of 727 degrees Celsius, the rate of heat radiated per unit area will be. That's the concept here. So in this question, we have to compare two temperatures and the heat radiated per unit area per second. That means we have to use the Stefan's law. Stefan's law, you know, heat energy radiated per second per unit area is proportional to 4th power of absolute temperature. So we have two temperatures and two energies. So we can say E1 by E2 is equal to T1 by T2 all power 4. So if you proportional and divide it, can be done like that. Now we have to find out E2 actually. So E2 you can write as E2 is equal to E1 into T2 by T1 power 4. So we have E1 is given there 5 into T2 is 727 degrees Celsius. You should convert to Kelvin. So plus 273 by T1 is 227 convert to Kelvin plus 273 power 4. That is 5 into this is 1000 divided by this is 500 all power 4. So if you cut it, it will become 2. 2 power 4 is 16. So 5 into 16, that is 80. So no need to convert the units. 80 calorie per centimeter square second. That is the energy radiated at a temperature 727 degrees Celsius. So here you should convert to Kelvin. That's take care. Though it is a ratio, you should convert and do it. If it is a difference, then no need to convert Celsius to Kelvin. Take it in mind. So I hope you got this videos clearly. Please prepare well. Best of luck for your company examinations.
Bright Education Center, Medical and Engineering Entrance Coaching Center, Hilal area, Doha, Qatar. For further enquiries, contact 306000679.